Today we're going to be looking at lesson 7.5, which is called Rational Exponents and Radicals. So the objective today is to rewrite expressions involving radicals and rational exponents. So let's take a look at what we have here. We have an N, there is a symbol, and then there's an A underneath it. We have vocab for each of these terms. So let's get to it. That little N, we call that the index. Okay, so it's going to be a number. It's on this symbol, which we call the radical sign. Sometimes you might also hear it referred to as the root, but it is a radical sign. So the index is on the radical sign, and underneath that radical sign, we call the radicand. So if you ever hear me saying any of those vocabulary words, that's what each of those pieces mean. Okay, so we're going to be using this radical sign, and there's going to be different numbers for indexes, and we're going to talk about how that relates to this term underneath it. If we notice, we have 5 squared equals 25. We would then say that 5 is a square root of 25. If I have 2 to the third power, if we think about our rules, remember that's like 2 times 2 times 2. That's why it equals 8. And so we would say 2 is a cubed root of 8. 3 to the fourth power, if you multiply 3 times 3 times 3 times 3, would get you 81. So we would say 3 is a fourth root of 81. So how the exponents are written in my problem, we have a 2. So that's why we're talking about a square root if I refer to it as a radical. We have a 3 for an exponent. So I call that a cubed root when we're talking about the radical. And then my exponent here is 4. We're talking about a fourth root of a radical. So that's kind of how they relate to each other. Therefore, notice that I can say that 5 equals the square root of 25, which another way to write it then as an exponent would be 25 to the 1/2 power. If we have 2, which is really the cubed root of 8, we can rewrite that as an exponent. It is 8 to the 1/3 power. And then 3 is the fourth root of 81, so we can write that as 81 to the 1/4 power. So hopefully you're kind of noticing a pattern here. So I want to go into the definition based off of this information right here. Okay, so in the box it says, if the nth root of A is a real number and n, which is the index, is a positive integer, meaning we're not going to make that little number connected to the radical a negative. It can only be a positive number. Then here is our formal definition. If I have a to the 1/n for my exponent, that is the same thing as the nth root of A. So we can rewrite exponents into radicals, or we can write radicals into exponent. And so that's going to be something that's super important in this lesson. We're going to look at some examples of rewriting going back and forth. So let's start by rewriting something that has an exponent, and we're going to turn it into what we call radical form. So it's going to have that root. Okay, so notice that we have several things to identify here. I have an x. When we're looking at it in an exponent terms, we call that the base. Okay, notice that my exponent is is 1/3. So that little number 3, which is in my denominator, when I rewrite it, that is now going to become the index. The base is going to get turned into the radicand So it's what's underneath that radical. So here's my radical. 3 is going to be a part of that radical because that's the index. The x is going to go underneath because the base turns into the radicand. And so that follows the definition that we just wrote. This is my final answer. If I take a look at the next one, we have 2x to the 1/7 power. Notice that in this problem, x is the original base to the exponent. 2, if you think about it, that has an exponent of a 1. It does not have the exponent of a 7th. So when we are rewriting things into radical form, you have to make sure you're only going to move the base underneath the radical if its exponent was a fraction. So because the 2 was not a part of that 1/7 for the exponent, the 2 is actually going to be staying outside of this radical. Notice that 7 is that little number that is going to become the index. So the 7 is going to be attached to that radical, and it is then the x that was the base that gets moved into becoming the radicand. So this would be my final answer. But then if you take a look at this third example, notice this time there are parentheses around the 2 and the x. That means that together that is the base. So because this whole entire thing is the base, that means that whole thing turns into becoming the radicand. So when I am thinking about what's going underneath this radical, both the 2 and the x does. So hopefully you notice the difference between what we had in the middle, where there were no parentheses, and now with the parentheses, they stick together. Notice that the denominator was an 11, so that becomes the index of this problem, and there's my final rewritten answer. So now let's do it the opposite way. Let me start with a radical and let's turn it into a base with an exponent, which we call exponential form. So notice that we want to start by identifying what the base is going to be in this problem. Well, the base starts underneath that radical. It is the radicand. So because that ends up becoming then the base, I'm going to have 18 to some power. Because it was a square, or not a square, but it was a radical, I'm going to have a fraction for my exponent. Looking at the index, this index is a 5. Indexes are the bottom of my fraction. So the top will be a 1. 18 to the 1/5 power is my final answer. Notice that in the next problem, what is underneath is an m, so that is going to become the base of my exponential term. So I'm going to have an m. Then I'm looking at the fact that I got to have a fraction for an exponent. I've got a little 8 for my index. That becomes the denominator of my fraction. The numerator is the number 1, so m to the 1/8 power. If I take a look at this third example, notice that we have 2 things that are underneath that radical. So we do want to make sure that we're careful. That means because both of those were underneath, I am going to want parentheses around that as my base. So I make sure that its exponent goes to both of those things. But remember, my exponent is going to be a fraction. The little index there is a 3 that goes in the denominator. The numerator is a 1. So without the parentheses, we would have a completely different answer. So notice that if there's more than one thing underneath that radical, put it in parentheses when you're rewriting it as a base. Moving along, let's take a look at rules for simplifying these types of problems. So we have 2 steps here. We want to rewrite the problem in radical form. Sometimes it might already be in radical form, which means step 1 was already done for us. But if it isn't, if we start with an exponent, we are going to rewrite it into radical form. The second step then is we are going to make a factor tree to group numbers based on the index. So remember, the index is that little tiny number that is a part of your radical. We're going to be grouping numbers that we make from our factor tree based off of that index. So let's talk about what that means with some examples. If I take a look at this first example, we have 3 under or with our radical, so that is the cubed root of 27. So notice this problem already is in that radical form. So step number 1 is already taken care of. We don't have to rewrite the problem. It's already in radical form. So moving on to step 2, it says make a factor tree to group numbers based off of the index. So to make a factor tree means I'm going to start by finding 2 numbers that multiply to 27. So you can use a calculator, you can use a multiplication chart. Hopefully we notice that 9 times 3 is going to multiply to give us 27. 9 is a number that I can keep breaking down. 2 numbers that multiply to 9 would be 3 and 3. But notice that I can't break the 3 down anymore. The only way to multiply to 3 is 1 times 3. This is called a prime number. So I'm always going to then end up circling my prime numbers. So notice that there are 3 circled numbers. I cannot extend this factor tree any further. But once again, notice that the number that I have for my index is a 3. So essentially that means we want 3 of the same number. And well, what do you notice? We've got 1, 2, 3 of the same number. The 9 you can ignore because we broke that up into 3 and 3. We made it more numbers. So there are no more numbers besides those 3. We were looking for 3 of the same numbers. I found 3 of the same numbers. The numbers that are the same happen to be the number 3, which means that 3 is my final answer. If we take a look at the second example, it is written as the 5th root of 32. So once again, the first step is to rewrite the problem in radical form, but this is already in radical form. So we're good to go. So we can start making that factor tree. So 2 numbers that multiply to 32. There's quite a few ways to break that down. One of those ways is 8 and 4. Neither one of these are those prime numbers I was talking about. I can keep breaking each of those down. Notice that 8 is 4 times 2. But 2 is one of those prime numbers. The only way to multiply to 2 is 1 and 2. And so I get to circle that. 4, you can break that up into 2 and 2. So notice that I circle the 2's because those are prime numbers. I get to ignore everything that got broken down. So notice that I've got a bunch of circled numbers. Well, if I'm looking at my index is the number 5. That means we want 5 of the same number. If I start counting up those 2's that are circled, I have 1, 2, 3, 4, 5 of them. So I have exactly what I am looking for. And because there are 5 2's, that means that 2 is my final answer. If we take a look at this next one, 64 to the 1/3 power. This time, it is not written in radical form. I see an exponent. So that's what I'm going to do first. I am going to rewrite this as a radical. So the 64, which is the base, gets moved underneath the radical. That denominator was a 3. That becomes the index. So now that I have it rewritten in radical form, I'm going to start breaking up the 64. And this time, my number is 3. So I'm looking for, once again, we want 3 of the same number. All right, so if I start thinking about numbers that multiply to 64, we have 8 and 8. Both of those I am able to break down further. 8 is 4 times 2, but I get to circle the 2 because that is a prime number. 4, though, we can break that down into 2 and 2. And once again, I get to circle those. Those are a prime number. So since I broke down the 4s and I broke down the 8s, I'm not looking at those. I'm focusing on the numbers that are circled. So let's start counting. Notice 1, 2, 3. That's what I want. I want 3 of the same number. So I have that once. I get to have a 2 as part of my final answer. But if I keep looking at those circled numbers, notice I've got 1, 2, 3 again. I've got 3 more 2s. So I've got another set of 3. So I have another 2 that I get to write a part of my final answer. I don't have any more circled numbers, so that takes care of this. All I have to do now is multiply those 2's back together. 2 times 2 is 4. So 4 would be my final answer. If I take a look at this next one, 256 to the 1/4 power starts as an exponent. Gotta get it turned into a radical. So with my radical, the base is going underneath. So 256. I want that index to be a 4. So once again, because that index is a 4, that means that we want 4 of the same number. So let's start breaking down the 256. There are plenty of ways to do it. One way is 16 times 16. I can continue to break down 16. Notice that 16 is 4 times 4. So even though we can keep breaking down the 4s, let's put a pause in this for a second. Let's count them up. Notice that there are 1, 2, 3, 4 4s. And notice that my index, I wanted 4 of the same number. So if you can recognize that, even though these are not what we call prime numbers, I found a group of 4 right away. And so I can say that my final answer is 4. If you kept breaking down those 4s, you would then have 2, 4, 6, 8 2s. And so essentially you would have 2 sets of 4, just like we had 2 sets of 2s in the last problem. So that's why we would then end up multiplying and we get back to 4. So a couple different ways to do it. Let's go ahead and move on then to the next definition. It says, if the nth root of a is a real number, and m and n are positive integers, then, and now here's my definition. We have a to the m over n exponent. That is going to equal n is my index, a is my radicand, but that whole thing is raised to the power of m. Or we can write it as the nth root, and then the exponent is underneath. So 2 different ways to write it, but this time we don't just have a 1 in the numerator of that fraction. We have an m, which means it can represent any positive real number. All right, so with that information, let's take a look at some examples. Let's rewrite into radical form. So I have x to the 2/9 power. So remember, the x is the base, so it's going to be going underneath the radical. Whatever that bottom number is in my fraction is my index. So now the only thing that's new is that there is a number other than 1 in the numerator. So we can then take that, put it in parentheses, and raise it to that power, and that would be my answer. Or the other way we can write it is that underneath that radical, which has an index of 9, we could then put the exponent with that radicand. So either one of these I would accept for an answer. In the second example, be careful. Notice that this first number of 4, technically, it has a positive 1 for an exponent. So that means that that number has nothing to do with going underneath the radical. So I have to keep the 4 on the outside. Underneath the radical, we know that we want the x because that is the only base that has the exponent that is a fraction. So the denominator of that is a 3. That's my index. I can put the 5 inside with the x. So that would be my answer. Or we would then have the 4 once again on the outside. And we would have that cubed root of x. But it's in parentheses. And it's being raised to that 5th power. So 2 different ways to write the same answer. Notice that in the next one, we do have parentheses, which means that entire term is going to go underneath the radical. So both the 2 and the n, because it was in parentheses, is a part of that radicand. And then we have 7 is the denominator. That whole thing is being raised to the 3rd power. When you have more than one thing inside the radical, if you were to write that 3 inside, it would have to look like this. You would want to keep the parentheses around both the 2 and the n, and then put the 3 on the inside. Okay, so 2 different ways to write that. Now let's rewrite it going the other way. I'm starting with the radical. Let's turn it into exponential form. So notice that the term that's underneath is an m, so that is my base. When I'm looking at my fraction, that 4 is in the denominator because that's where the index goes. The 3 goes in the numerator, so m to the 3/4 power is my answer. In the next example, we have 2 underneath. That is now going to be the base. If I'm thinking about my fraction, 6 is the index that goes in the denominator, and we have then the 11 on the top. So 2 to the 11 over 6 is my answer. All right. Notice that in this case, we have 2g squared under the radical. So 2g squared is going to be the base. But because they both are going to be the base, there's got to be parentheses around it. Notice that my index is a 3. Okay, notice that I kept that 2 in the parentheses with the g. Because it didn't have anything to do with that other base, which was a 2, I can't move that 2 out as an exponent with the 3. I'm going to have to put a 1 because technically that's what this whole thing was being raised to. It's being raised to the 1st power. All right, on the next page, let's talk about then how we would do problems like this. We have 8 to the 2/3 power. I want to follow the rules like we did in those previous problems. I want to first rewrite this into radical form. So we are going to have 8 underneath that underneath that radical. 3 is the index. And let's think about then having the 2. Let's do this. Let's put the 2 underneath it. Okay, because now that I know that underneath that radical 8 is being squared, we can go ahead and we can square that. 8 squared is 8 times 8. That gives you then technically the number 64 under that radical. So then if I start breaking up the 64, if you look at my radical, I have an index of 3. So that tells me that we want 3 of the same number. Many different ways to break up the 64. One of the ways would be 4 times 16. Notice that 16 is 4 times 4. So if I want 3 of the same number and I broke the 16 down, notice that there's 1, 2, 3 of the same number. So that means I can technically stop at this point. Because 4 is the number repeated 3 times, 4 is going to be my answer. If we look at this next one, we have underneath the radical, we have the 9. Because that bottom is a 2, that's technically going to be the index. And let's put the 5 with the 9. Now, even if you don't write the 2, it's technically the same thing. That's just representing the square root. So these two things relate to each other. So 2 is the only number that you technically don't have to write as an index, and you still have the same answer. All right, so let's think about this. We want to simplify. So just like the last problem, we took 8 squared and we multiplied it out to get 64. Let's think about this for a second. Because it's 9 to the 5th power, that's 9 times 9 times 9 times 9 times 9. It's written out 5 times. Because my index is 2, remember, that means I want 2 of the same number. So without me actually multiplying all of those 9s together, let's look at this. Here is a pair of 2s that are the same number. Here is another pair of 2s that are the same number. When I have 2 of the same number, they end up moving outside of the radical. So I'm going to have a 9, not once, but I'm going to have it twice outside. There is still a single 9 that is left over underneath that radical. So when I multiply 9 times 9, that gives me 81. And now we have a 9 underneath that square root. So can we keep breaking up 9 and still find, because it's technically an index of 2, can I still find 2 of the same numbers that multiply now just to the number 9? Well, the answer is yes, 3 and 3. So because I was able to find that, the 81 is now going to be multiplied by the 3, because that gets moved to the outside. 81 times 3 is going to give us 243. And that would be my final answer. Finally, in the last one here, we have 32 to the 2/5 power. So if I think about rewriting it into exponential form, the 32 is going to be under the radical. Its index is 5 because that's the denominator. And we then technically have that 32 being squared. So that means that underneath that 5th root, we really have 32 times 32. Now, because my index is a 5, that means we want 5 of the same number in order to move it outside of the radical. So let's start with the first 32. Two numbers that multiply to 32 would be 8 and 4. We can break down 8 into 4 and 2, but 2 can't get broken down any further. 4 is 2 times 2. All right, so looking at that, I can ignore the 4s and the 8s because I broke those down. And if I count it up, 1, 2, 3, 4, 5, we found 5 of the same number. So I get to move a 2 outside of the radical. But if you notice, that was just one of those numbers underneath the radical. We got to do the same thing. We have another 32. So hopefully you notice that if I broke it down, it would get broken down the exact same way. So I get to ignore the 4s and the 8s. And if I count 1, 2, 3, 4, 5, there are 5 2s again. So I get to move another 2 to the outside. So notice that this first 2 came from all the yellows that got highlighted. And then the second 2 comes from the second group of 2s that got highlighted because we found 5 of the same number. So just multiply these together. 2 times 2 gives me 4. That is my final answer.